Okay. All right. Hello everyone. Welcome to my presentation. I'm actually not Xiaotao because of some time conflict. So I'm giving his talk and he gives mine on Monday. We work together in the same group in Ivan Bozovic's group in Brookhaven National Lab. So I would like to thank the conference organizer for this great opportunity. And I would like to thank you all for coming to my talk today. So the topic of my talk is the method to probe the interfaces issues in CUPRATE, these tri-layer junction lanthanol strontium CUPRATE, copper oxide, lanthanol strontium aluminum oxide, and the lanthanol strontium CUPRATE oxide, this trilayer junction. Okay, here is my motivation. So the motivation of my work is to create Josephson junctions, more precisely high TC superconductor insulator superconductor Josephson junctions. Because these junctions are the main circuit element if you want to create a superconducting seam of a quantum computer. Currently, majority of these kind of junctions are fabricated with conventional superconductors. It's relatively easier to achieve since the coherence length is relatively long at hundreds of nanometers. But in our case, if we want to use high TC superconductors, it's a little bit more difficult. Well, a lot more difficult because this superconductor itself is a complex oxide, so it's difficult to grow. It's very complex. And the coherence length of the material is very short. It's only 1 nanometer. So in order to make such a small barrier layer is very difficult. And it's also very difficult to find the correct material to be this specific barrier layer. And this superconductor is D wave, so we have to take into account the D wave pairing symmetry. Also, as a oxide, it may has oxygen desorption and many other issues. So it's a quite scientific material science challenge for us, and so we have been doing or trying to find the correct or good barrier for a long time. This is our previous work, but dating back to 2003. And at that time, we used lanthanol copper oxide without strontium doping as a barrier. And even with just one layer, one unit cell actually of lanthanol copper oxide as a barrier, there's no supercurrent observed. Even though from the magnetic susceptibility measurement, we can see the lanthanol strontium CUPRATE itself is superconducting, but somehow just one layer of this lanthanol CUPRATE barrier can block the supercurrent. Over these years, we are experimenting with different technique and different growth technique in the barriers. And before I get into our current recent result, I would like to first to show our experimental setup and equipment at the Brookhaven National Lab. We use this atomic layer by layer molecular epitaxy machine at the Brookhaven National Lab. You can see it's quite a complex machine. We have 16. Each of these arm is a K-cell source, or you can use E-beam as well. And we have QCM to measure the rate of each source. And we have a read. We also have different other methods to monitor our growth. And we use pure ozone, which is in the back here, use distillation to get pure ozone as our oxidizer. And the advantage of this system is that every single section of the system is modularized. So each small section, like each of the arm, can be closed off with a gate valve, and each of these, for example, this single arm has its own pumping system with a dry pre-pump and a turbo molecular pump. So we can do maintenance work, we can do repair of a small section of the chamber without breaking the vacuum of the whole chamber. In this case, we can significantly improve the productivity. And we would like to show like our normal quality of the film we can grow. So during grow, the main and the most important method that we monitor our growth is the read. If we look at our read pattern and the read oscillation, we can see each layer, the crystallinity structure is very good because you can see the long and very sharp main streak, and which shows it's a two-dimensional growth without 3D islands. And we can see the main specular spot is very bright, and we can see, if you see closely, you can see these Kikuchi lines. And we can see even secondary Loy circle reflection. This is a good testament. If we see this during our growth, we know we have a good growth, so then we keep growing. And from the oscillation, the read intensity, this is basically the monitoring the intensity of this specular spot, and the intensity will oscillate during the growth. We know exactly how many layers we are growing, and you can see the maximum intensity stay mostly constant, which means during the whole growth process, the smoothness of the film is very good, and we can keep growing. During this whole process, the smoothness of the sample will not diminish. And after the growth, we'll do various different characterizations. Our most important ones shown here are AFM. And if you look at the AFM, we can see the sample, our film follows the atomic terraces or atomic steps, each of these, following the substrate, the atomic terraces of the substrate. And the roughness is very good at 0.17 nanometers. And if you have a secondary phase, you can see it in AFM. If you have like a 3D defects, which has a different structure, you can see it. And now in this, if we have a good growth, then we don't have it. And the next important one is the mutual inductance technique. This technique shows the we basically measure the masonry effect when the film becomes superconducting, and this shows the exact TC with high precision, and we can also monitor like superfluid density after it goes superconducting. And this also shows the quality of our film. The peak, the transition is extremely sharp. The full width half maximum is at 0.3 Kelvin. This shows at a scale of 10 millimeters square, our sample is very homogeneous, with which have a very homogeneous TC. And now we are trying to find a different barrier for the SIS junctions. This time, our prime candidate is the lanthanum-strontium aluminate. The reason we choose lanthanum-strontium aluminate is very similar that we choose lanthanum-strontium aluminate as our substrate. They have the same crystal structure. as the lanthanol strontium cuprate, and the lattice mismatch is very minimal, and it's relatively electrostatically compatible. So, and the very important point is lanthanol strontium aluminate is a very good insulator. So we hope if we can grow a structure that have this lanthanol strontium aluminate in between the lanthanol strontium cuprate, we hope it can be a good barrier. Now, here is the issue we are facing if we are choosing lanthanol strontium aluminate as our barrier, is that because we use it as substrate, so we know it may create some dead layers of lanthanol strontium cuprate when this lanthanol strontium cuprate is very close to the lanthanol strontium aluminate. Now we are trying to find out exactly how many layers are the dead layer, because together with the dead layer and the lanthanol strontium aluminate, it will be our actual barrier thickness. Now, to identify that, we designed the system to grow, which is a superlattice system. So on top of the lanthanol strontium aluminate substrate, we grow certain layer of optimum doped, OP stands for optimum doped lanthanol strontium cuprate. Then we grow one layer of lanthanol strontium aluminate. Then we grow optimum doped layer again. So several stack of these structures. And we can vary how many layers we put in between the lanthanol strontium aluminate. Then with this, we can pinpoint exactly how many data layers we have. So here is the read pattern during the growth. So what we can see is this kind of surface. We can see the main peak. And this is the read pattern for the optimum doped lanthanol strontium cuprate. This is the read pattern when we grow one layer of lanthanol strontium aluminate. Then we switch back to optimum doped cuprate. And by the second layer of optimum doped cuprate, you can see the surface reconstruction comes back. And during the whole process, we can see the main peak stay the same. And that shows, and they are still very sharp and long, which shows the growth stay two-dimensional, and we can recover the surface reconstruction of the optimum doped cuprate, and there's no second phase precipitates during the whole growth. And if we look at the read oscillation of these kind of growth, we can clearly see where the lanthanol strontium aluminate is. And first of all, the overall intensity of the specular spot stay pretty much constant, which means the sample stay smooth during the whole process. And this clear difference of the read intensity shows we have a very sharp interface. So if we look at the film we grow, from the AFM, we can see the surface still stay very smooth with a roughness of 0.3 nanometer, and the sample growth still follows the atomic steps, atomic terraces of the substrate. And if we look at the mutual inductance of the sample we grow, if we have a relatively high number of optimum dope sandwiched between the lanthanol strontium aluminate, this lanthanol strontium aluminate plus 5 optimum dope, which means there are 5 optimum doped layer of lanthanol strontium cuprate sandwiched between 2 layers of lanthanol strontium aluminate. And this M is heavily overdoped. I will talk about this later. So in these two situations, we can see relatively higher TC at 30 Kelvin, and the transition is very sharp at full width half maximum at around 1.5 Kelvin. Shows the film is very homogeneous throughout the 10 millimeter times 10 millimeter square scale. And to verify we have a superlattice growth, we collaborate with the very good the world-class TM group at BNL. So Dr. NJ Han and the Yimei Zhu performed the TM cross-section TM study of our sample, and we can clearly see the superlattice structure. And it's exactly what we intended to grow. So we have 5 layers of optimum doped, then 1 layer of lanthanol strontium aluminate, and so forth. So they even did an element mapping for us. We can clearly see at where the lanthanol strontium aluminate is. We have a lower layer. We have almost no copper, and where we have lanthanol strontium CUPRATE, we have copper, and at this lanthanol strontium aluminate, we have a higher amount of strontium because in lanthanol strontium aluminate, the ratio between lanthanol and the strontium is 1:1, and in optimum doped lanthanol strontium CUPRATE, the lanthanol strontium ratio is 1.82 to 0.16. So in lanthanol strontium CUPRATE optimum doped, the strontium concentration is much lower than in lanthanol strontium aluminate. And so we can see in lanthanol strontium aluminate, the concentration of lanthanol is lower. However, we don't see clear the signature of the aluminum. We have several theory why that's the case. In the future, we are going to improve the sample preparation for the TM sample, hopefully to solve this issue. But for the preliminary results, I think this shows a very good TM image to show we actually have a superlattice structure. So here is the TC we measured from mutual inductance. So if we have 2 layers of optimum doped CUPRATE sandwiched between lanthanol strontium aluminate, we have a TC which is lower than 4 Kelvin. If we make it to 3 layers, then we have 5 Kelvin. If we make it to 4 layers of optimum doped, we have 6 Kelvin. And when the magical number becomes 5, when we have 5, then immediately we have 30 Kelvin of TC. And we are trying to understand it. And here we define this L1, L2, and L3. L1 means the lanthanol strontium CUPRATE, optimum doped lanthanol strontium CUPRATE, is in direct contact next to lanthanol strontium aluminate. L2 means is the second adjacent from the lanthanol strontium aluminate, and L3, which means there are 2 layers of lanthanol strontium aluminate. Then you see the lanthanol strontium CUPRATE, then you see the lanthanol strontium aluminate. So in this case, because of the different mutual inductance measurement we performed, we infer that this L1, which is directly close to the lanthanol strontium aluminate, will have a very low TC smaller than 4 Kelvin. And L2 will have maybe 5 to 6 Kelvin of TC. And when the optimal layer or optimal doped cuprate is 2 layers away from the lanthanol strontium aluminate, then it restore back to 30 Kelvin of TC. So in this case, we have 1, 2, 3, 4, 5 layers of barrier. And to further understand this, we performed the transport measurement. And we did this whole bar patterning. So each sample we have 6 different devices, and we use a 4-point method, reversible 4-point method to measure the sheet resistance of our sample. So these are the 6 different device we have on the same sample with a different size. And so we have a current flow, then we measure voltage at a different point and use the 4-point method to measure resistance. And from the size of this whole bar, we can calculate the sheet resistance. And we know exactly the thickness of the sample we grow, so that's how we calculate the sheet resistance. And this shows how the sheet resistance changes with how many optimal layer of sample we have in between the lanthanol strontium aluminate. We can clearly see when we have 5 layers, then the resistance is very comparable to the optimal doped sample. And when we only have 2 or 3 layer of optimal doped sample sandwiched between lanthanol strontium aluminate, the resistance increase significantly. And these collaborates with the TC we observe in the mutual inductance. Now, we are trying to simplify it and use a model to estimate the resistance of each different kind of optimal doped lanthanol cuprate when it depends on how close it is to the lanthanol strontium aluminate. So this is the simple model we propose. We assume because of the current flow in plane, and each of the layer of the optimal doped lanthanol cuprate is separated. So we assume they don't interact with each other, and they only show the current only flow in plane in the optimal doped layer, and current evenly distributed through different, this is one stack because it's a superlattice sample, so we have different many stacks, and we assume the current is evenly distributed. Then with this, we can estimate the resistance of different kind of cuprate, optimal doped cuprate L1, which is directly next to the lanthanol aluminate again, and L2, which is second adjacent to the lanthanol aluminate, and L3 is the third adjacent to the lanthanol aluminate. So we consider them are in parallel, then we can calculate or estimate the exactly resistivity of different kinds of L1, L2, L3 of the optimum doped lanthanol strontium cuprate. And we can see this is the result. And it seems when the lanthanol strontium cuprate is close to the lanthanol strontium aluminate, L1, L2, they kind of show a signature of underdoped lanthanol strontium cuprate. And this number are actually very close to, or at least very comparable to those in the bulk lanthanol strontium cuprate crystals with the similar TC. And then we are trying to improve it, trying to protect the optimum doped lanthanol strontium cuprate, which effectively reduce the thickness of the dead layer. This is the first step we tried, that is use a heavily overdoped lanthanum strontium CUPRATE to protect the optimum dope. So instead of growing two optimum doped layer, we grow a very heavily overdoped lanthanum strontium CUPRATE, which is a strange metal, but for in this case they are not superconducting, so they are metallic, and we grow this kind of structure. So in the next case, when we only have two layers of optimum doped lanthanum strontium CUPRATE, instead of putting one layer of optimum dope, if we put a one layer of metallic sample, this actually significantly increased the TC. And when we only have three layers of optimum dope and protected by the M, and we significantly increase the TC back to 30 Kelvin. So it seems by implementing one metallic layer that's separating the lanthanum strontium aluminate and the optimum doped lanthanum strontium CUPRATE, it will improve or help reduce the thickness of the dead layer. So we are still experimenting and try to understand the effectiveness, why it can do that. And we are also trying different structures to help minimize the thickness of the dead layer. But this is what we achieved so far. So in summary, we are trying to fabricate a C-axis tunneling of these lanthanum. So we are trying to fabricate SIS junction from high TC superconductors, and we use this superlattice test method to find out exactly how many dead layers we have. And we find out there are two dead layers next to the lanthanum strontium aluminum, and if we use the overdoped lanthanum strontium CUPRATE, it can actually protect the optimum doped layer and reduce the effectiveness of the barrier thickness. So that's the end of my talk. Thank you very much.
Thank you, Xi. We are open for questions. Are there any questions? Please.
Thank you. It's a really interesting talk. And I have a question.
Thank you.
It's really interesting because all high TC can be used as a Josephson junction devices. My question is, did you look to the C-axis behavior of this Josephson junction? You show the RT behavior, just show the in-plane resistivity, right?
Yes, you are very correct. We actually have pattern, and we are studying the C-axis. The initial result is there is no supercurrent that have been seen. That's why we are trying to reduce the number of the dead layers and optimize the result, and then maybe even try different barrier materials. But we did try, and we haven't seen the supercurrent.
Can I ask the second question? If you use again another overdope regime at the top of the dead layer, for example, and as I remember, you use only one dead layer just up to on this insulating layer. If you use the second overdope the layer just next to the following the insulating layer, maybe you can enhance the TC, and also maybe you can observe. Can you also expect some kind of the critical current behavior?
We actually are doing this kind of experiment. We have many other different structure that we have grown with different M layers, even other kind of sample we have grown. So so far, it actually enhances the TC, but not by much. And still, the M layer is also a dead layer. It's not a superconducting, so it's also a barrier. So if you use two, it's not effectively reducing the actual numbers of the or thickness of the barrier. So we still haven't seen the supercurrent yet. And there is a follow-up experiment we are doing right now. Different layer of M has been tried.
Okay, thank you. Are there any questions? No? Okay, thank you to the speaker. Actually,
Thank you.
we are sending the certificate from the online.